In the last section, we talked about drawing Lewis structures, and you based a Lewis structure, the correctness of the Lewis structure, based on whether or not it followed the octet rule. Something that we didn't consider, though, is what if there's more than one way to draw a Lewis structure while it still follows the octet rule? And this can actually happen. So in order to determine the best way to draw a Lewis structure, if you have more than one structure that follows the octet rule, is by using formal charges. Now, the official definition of a formal charge is the charge the atom would have if all the atoms in the molecule had the same electronegativity. Now, this is not the case. However, the formal charge just serves as a bookkeeping effort in order to decide what is the best way of drawing a Lewis structure. So here's how we actually determine formal charge, and then we're going to apply it to an example. So, for a formal charge, there are two different ways of determining the number of electrons that are assigned to an atom. The first is any of the unshared electrons, and those are the electrons that are not bound, that are not part of a covalent bond. And you just provide that specific number of electrons. So let's say, for example, I have 4 unshared electrons. That would represent 4 electrons that I'm going to assign to the atom. For the second one, for any bond, whether it's single, double, or triple, you count half of the bonding electrons and you assign that to the atom. So for example, if I have a single bond, instead of being 2 electrons, I would assign an atom just 1 electron. Remember, I can do that because for formal charge, I'm assuming that the atoms have the same electronegativity and therefore they are sharing the electrons equally. So remember, unshared electrons, just the number of electrons that are there. For a bond, it is half the number of bonding electrons. And so to calculate formal charge, all you need to do is subtract the number of electrons that are assigned to the atom from the number of valence electrons in the neutral atom. Okay? We're going to do that in just 1 second. Just keep in mind that formula for finding formal charge. Here is how we actually determine which Lewis structure is correct or is the best fit. First, we call it the dominant Lewis structure, right? The one that is the best fit. The dominant Lewis structure is the one in which the atoms bear formal charges close to 0. So if I have one Lewis structure that has a +1 and a -1 for formal charges, while for another one I have a +4 and a -4, obviously the first Lewis structure would be the dominant one. Second, a Lewis structure is dominant if the negative charge resides on the more electronegative atom and the positive charge resides on the less electronegative atom. So for example, if I had hydrogen and fluorine had a positive formal charge, I would know that that Lewis structure was not dominant because fluorine is more electronegative than hydrogen, and therefore the formal charge of fluorine should be negative while the formal charge of hydrogen should be positive. So we're going to work through this example of CO2 in order to take all of these concepts and make them make more sense. So I'm going to go through and look at this first example in which there are 2 double bonds for carbon dioxide. If you look at the first oxygen on the left-hand side, oxygen has 6 valence electrons, always. So we put 6 for the number of valence electrons. To determine the number of electrons that are assigned to the atom, we have 4 electrons that are unshared, and then we have 2 double bonds. So 4 electrons for the unshared, and then 2 double bonds that represents just 2 electrons. So I have a total of 6 electrons that are assigned to the atom. So my formal charge, once I subtract the valence electrons from the electrons assigned to the atom, would be 0. For carbon, carbon has 4 valence electrons. If you notice, there are 1, 2, 3, 4 bonds between carbon and the 2 different oxygens. Therefore, the number of electrons that are assigned to carbon would be 4, and therefore the formal charge would be 0. For the last oxygen, it's the same thing. Oxygen has 6 valence electrons. There are 4 unshared electrons, 2 pairs of shared ones. Therefore, I have a total of 6 electrons that are assigned to the atom. Therefore, all of the formal charges in this case are 0. If you look at the other example, because both of these Lewis structures follow the octet rule, if we look at this one, I've got, for the first oxygen, I've got 6 valence electrons always, and then I have 2, 4, 6 unshared electrons and 1 pair of shared electrons, therefore 6 plus 1 gives me 7, therefore the formal charge of oxygen is -1. For carbon, I still have 4 valence electrons, and I've got 4 electrons assigned from the shared, or the bonds, therefore my formal charge is 0. And then on the right-hand side oxygen, I have 2 pairs of unshared electrons, and then 3 bonds, therefore I have a total of 5 electrons that are assigned to the atom, and therefore my formal charge is +1. So if we compare these two, if I didn't know about formal charge, I would say that both of these Lewis structures are valid, and they are. However, the first Lewis structure, because all of the formal charges are 0, that first Lewis structure is the dominant structure, the one that you will see more than the one on the right-hand side. In the last section, we talked about the fact that there can be multiple Lewis structures that all follow the octet rule. Now, another exception when we're drawing Lewis structures is resonance structures. And I'm going to explain what a resonance structure is in just one second. But what I want you to do first is to draw the Lewis structure for O3, for ozone. So pause this video right now and please do that. What you should have noticed when you were drawing O3 is the fact that you need just one double bond in order to follow the octet rule. So as you can see in this drawing right here, for one of these versions I have the double bond on the left-hand side, and for the other one I have it on the right-hand side. So the question that should come to your mind is, well, how do I know where to put that double bond? And the answer is that both of those Lewis structures that you see in front of you with that double arrow in between them, those are both correct. And so when you have more than one way to draw a Lewis structure, like you do in this case with O3, you have a resonance structure. Now, a big misconception with resonance structures is that half the time O3 exists in the form that you see on the left-hand side, and then the other half of the time it exists like you see it on the right-hand side. And that's actually not the case. Instead, O3 exists as a blending of those two Lewis structures. And it's kind of hard to imagine as a blending or a mixture of the two until you think of this example. If I have blue and yellow, which are two very different primary colors, when I blend them together, I get the color green. And so with O3, I don't have one double bond and one single bond. I have a blending of the two. There are additional exceptions to the octet rule, and we're going to look at them very briefly right now. And when we look at the Vesper theory and we look at molecular geometries in the next section, then we will actually get more into detail with these exceptions, especially the third one. The first exception is when you have an odd number of electrons. Up until this point, the number of valence electrons that you've had has always been even. But there are some instances in which you can have an odd number of valence electrons. So for example, NO, as you can see there are two different versions of NO. What I would like you to do actually is to decide which Lewis structure is more valid. So think about what we talked about at the beginning of this video and figure out which is the dominant structure. Okay, so that's one example of an exception, odd numbers of electrons. So you can pause the video to do that, and then I'll continue on. The second exception is when you have less than an octet of valence electrons around the central atom. Now the two elements that tends to happen for are boron and beryllium. And so I'm going to show you right now an example for boron. This is the dominant Lewis structure for boron. Notice boron only has 6 valence electrons around it. This is another way of drawing the Lewis structure, but as you notice, looking at the formal charges, the first one, fluorine, has a +1 formal charge. That should not be the case because fluorine is more electronegative than boron, so that's not a valid Lewis structure. That's not the dominant Lewis structure. And you can look at the other examples. These three right here, these are actually resonance structures of each other. These are not the dominant structure. Instead, the one on the left-hand side, which actually breaks the octet rule, is the dominant structure based on formal charge analysis. The third exception is when you have more than an octet of valence electrons. So instead of having just 4 items bound to the central atom, you can even have up to 6. And we'll look at that when we look at molecular geometries. Now, the interesting thing for you to know atoms, central atoms that are above the third period, they do not have this exception. The reason why atoms in the third period and below are able to have more than an octet of valence electrons is because they have a d orbital which can be used for bonding. Finally, you're more likely to have an expanded valence shell if your central atom is large and the atoms that the central atom is bound to are small. So atoms, central atoms that are large and that have small atoms that are going to be bound to them, they are better able to fit more atoms and therefore are able to have much more than just an octet of valence electrons around them.